Hello everyone, welcome to a new class. In today's video, we will talk about how to perform an exploratory data analysis using images. So, in our previous classes, we mentioned how important it's unstructured data. Remember that around 80 up to 90% of the data in the world is unstructured. That means text, images, or videos. So it's important that we know how to analyze this type of data. Now, when we talk about images from this type of data, we can get a lot of information, such as the colors, shapes, textures, patterns. So, for example, for shapes, we can identify if you think about Tesla cars, they can identify the shape of the traffic sign, also the color, to make decisions, right? To stop the car or decide which is the best course of action. Same thing with shapes. We can identify objects in an image. We can identify whether it's an anomaly, if there is a disease using an image. Okay, so it is important for us to learn how to work with this type of data. We need the tools to visualize, to perform EDAs, and of course, the modeling part. So typically, when you work with images, most of the examples that you mentioned, it's classification, where the output is a class, you want to predict something, it is a class. So for example, when we talk about in healthcare, most of the applications that you see, it's about classification, like whether the person has a disease or not. But there is also object detection, like a typical data identification. There are different problems when we're working with images. So here there is a sample of some applications that are very common. So yeah, I already mentioned in computer vision, of course, the classification problems, object detection. Object detection is also for in videos. I'm pretty sure that you have seen those cameras, and when you're watching like the video in real time, it identifies the objects. It places like a rectangles, like in the objects that it identifies. Okay, in what other settings we can use image analytics? Think about in agriculture, there is something called precision agriculture, where using images, like from using a drone or from satellites, it is possible to identify whether the soil needs water or some other nutrients in order to maximize the crop yield. In security, there are multiple applications, facial recognition, for surveillance, for anomaly detection. So there are in different areas there are multiple applications, and this is growing. Okay, but when we talk about images and when we want to analyze them, it is important to know some concepts. So pixel, I'm pretty sure that all of you are familiar. We have heard multiple times the word pixel. So what is a pixel? So it's short for a picture element. So that's where the PI is for picture, the EL is for element. So it's the smallest possible unit of an image. And these pixels, they capture the color. So when you see numbers associated to a pixel, those numbers are giving you information about the colors that are in that pixel. Now, if you have like a one channel pixel, that's what we call grayscale image, only black and white. So in the one channel, each pixel will have a single value. It will go from 0 up to 255. So if the value is equal to 0, it's black or dark. If it's close to 255, then it's going to be white. Now, it is possible, of course, when you have an image with colors, so that will be a 3 channels. And typically, you have seen this notation RGB, that's red, green, blue. So in this case, each pixel will have 3 numbers: the red number, the green, and the blue. So it gives you an idea the which color is located in that specific pixel. So let me ask you a question. We have here a picture of the dog, and the dimensions is 650, that's the height, and the width is 450. Now, how many pixels we have here? So the number of pixels will be given by this multiplication. So that's close to 300,000 pixels. That's a lot, even though this is a simple image. Now, each pixel in this specific case, because this is a grayscale or one channel pixels, then in this case, this is we have 300, almost 300,000 variables only for a single picture. So look at the complexity. Even though it's a small picture, simple picture, since the dimensions are 650 by 450, then the number of variables is close to 300,000 variables. So the complexity of these problems are higher compared to just numerical variables, right? Or even categorical variables. So that's important to know, because when you have data with color, images with color like this one, where there are three channels, RG and B, then even the same image size, 650 by 450, but now there are like three dimensions, right? Because it's like three colors per pixel. So here the number of variables is close to is three times the previous picture. So it increases, right? If it's almost 300,000, now it's going to be like almost 900,000 of variables. So the complexity is higher. That's why it's typical, it's very common in these settings that we reduce the dimensionality of the images just by going from a full color image to a black and white image, because you decrease the complexity. We get rid of a lot of variables when we do that conversion, especially when you're doing an EDA. You explore all those possibilities. So then an image is just it's unstructured data, and it's represented as a matrix of pixels. So this is how it looks. Look at the 8, a digit 8 here, that's the image. Now the representation using the values of the pixels is, you will see it to the right. So 0 means that it's black, it's dark, right? As the value increases, then you get closer to a white color for that specific pixel. So you can see here with the numbers, you see a shape, right? You see a shape because that this is a small picture, so it's easy to visualize the shape here, and it's not a complex shape. Now, when you're gonna when you visualize the image, that's what we see. But when you're gonna process it using a computer, using an algorithm, a neural network, so you need to do the translation, and you use this information, the values in the pixels, like these metrics that you see here. Now, this is very important because thanks to this type of data is that you can analyze shapes, because you see how the color the number changes. So for example here, let me add the pen here. For example, in this part of the picture, you have 16, so it's close to dark, but then next to that value there is a 118, right? So you can see here, you see a difference. This is 2, 14, 16, 4. These are close to 0. But then next to that value, there is 98, 70, 119. So it means that there is a change of color. So that's how you identify shapes, right, in an image, by looking at that. Now, you won't do it manually, right? Of course, the algorithm is going to identify the pattern by looking at those changes in the colors, right? That's how you're going to identify a circle, a square, a rectangle, different patterns, right? Or different colors. Okay, so dimensionality reduction, it's important when you're working with images, because the original file typically they are gonna require a lot of storage. Also, if you keep the original images, the processing times for in your analysis, if you are creating a model, they're gonna be higher, right? It's gonna take like more time. So what are the possibilities to reduce the dimensionality? Well, I mentioned going from like color to grayscale. That's one option. It's gonna reduce the number of variables. Like it's gonna divide them by three. But there are other possibilities. So when you, for example, when you resize an image, so when you make it smaller, you reduce the number of pixels. So if instead of for example this one 650 by 450, you have something like 100 by 100. So you go from almost 300,000 variables to just 10,000 variables. So that's also an option to resize your image. That will depend, of course, of the problem. Grayscale, we already mentioned that one. You can do PCA, principal component analysis. That's also a possibility. Actually, in the example, we will do that. We will apply principal component analysis to be able to see if the problem is possible to create a classification model. And of course, there are other methods using neural networks, such as encoders, that will help us to perform dimensionality reduction. Now, if you're going to perform an EDA, what are like the basic questions that you want to answer. Of course, depending on the context, you will add more questions, but some of the basic questions in general are: what are the image dimensions, the height, the width, how many channels. So this will give you an idea of the number of variables that you have per observation. In real life, sometimes our data sets are messy. So it's possible that images are different. They have different sizes. So you need to ensure that all of them have the same size, because that might affect when you're training your models. So that's important to check the height, the width. That's how you can identify, like a typical images. Something common, very common. I'm sure that when you have like downloaded the images to your computer, at some point, maybe there is like a picture that the storage is, it's the file size is like 0 kilobytes. When you try to open it, of course it won't open it. It's corrupted. So things like that you need to check when you are performing the EDA. Another thing that you will do is to analyze the distribution of pixels. So like how many pixels are close to 0, close to 255, or in the middle ranges. And if there are like variations of the color, uh, this will help you to identify whether there are some images that are corrupted or affected. Maybe they are blurry, too dark, or too, like or too white. Another important question to answer, especially if you're carrying out like you want to create a classification model, it's always important to check for the classes that you want to predict. It's important to know whether the class is on balance or not. Okay, there are a lot of challenges when we are working with images as data. So data collection, it's a challenge. It's expensive and slow. Let me show you an example. This was a project. I was the advisor. So this was for a master student. This student, she works for a company, and they buy like medical products. And her interest was in trying to measure human parts, like the what is the length of the arm, the length of the leg, for example, or just some specific part, maybe just the hand. Or why? Because they were analyzing prosthetics, arms, legs, and hands. So the challenge is some of the customers, they were in different cities. Even they were in some cases small towns. So for the customer, it was difficult to come to their location, and also for them, it's expensive, like to send someone just to measure the patient. So one of the things that they are exploring is and that's the thesis, to create a model that is able to measure the parts with an image, with a couple of images of the same person. Now there are challenges here because they have a lot of variability, a lot of noise. Because in some cases, when the person takes a picture, so they have different cell phones, so the resolutions are going to be different. Also, in the background, there were objects in some cases, other people, and that affects your analysis, right? Because you need to clean your data. The pre-processing here is a little bit more challenging. Also, some people were like, look at this. For example, here there is like a shoe in the image. So, or there were objects affecting the person. Also, in some cases, when they take the picture, they were too close to the camera, or sometimes they were too far from the camera. So you need to resize, you need to kind of like crop the picture to ensure that all of the pictures they are like similar. At least they are kind of like all center. So the analysis makes a little bit more sense. So it's challenging. You have a lot of variability, a lot of noise for sure. It's expensive, the data collection part. In some cases, the labeling is a challenge, especially when you want to create a supervised model, regression or analysis or regression or classification. You need your images to be labeled. For example, if you want to predict a disease, your data set originally you need maybe with experts. They will take the images and you need to label them because the model has to learn. So for the model to learn, it needs some cases, right? Some outputs, non-outputs. So it will be able to identify the relationship between the inputs and the outputs. So the labeling is a challenge. High dimensionality, for sure, that's the one of the main problems with images. As we mentioned before, with small images, like just 100 by 100, there were 10,000 variables. So this is always a problem with the resources that you need to process that data. Data leakage, this is an important one. I remember that was many years ago, like almost 5 years or a little bit more. And this was like a top team, like they were doing research and they were predicting, they were identifying tumors. I think it was like brain tumors, if I'm not wrong, but it was about tumors. What was the problem? So typically, in our previous examples, previous models, when you have numerical data, so one of the observations are independent. You just have one observation. But in healthcare settings, it is possible that for a single subject, for a single individual, you might have multiple images, right? It's like in the project that I just show you, it's possible that the same person, you take, like a front picture or a picture just looking at the right side, left side, or from behind. So there are multiple angles, right? So same thing with images, with X-rays. It is possible to have multiple angles. So the problem in that case is that when they were doing the splitting of the data in test and training, they had some observations, some images of the same patient in the training, but also some images of the same patient in the test set. So the model, the algorithm is smart, like it was able to identify that, and the model was overfitting. So it was good at predicting in the test set, but then in real life it's not that good because when it's difficult for the algorithm to find the same individual in both sets, then of course the performance is gonna drop. So that was a problem. The good thing is that the authors they recognize the issue, the error, and I remember they have to fix the paper, like redo the all the splitting and all the things. But at the end, they got the results in the correct way, and it was a lesson for everyone about the data leakage. All right. So what are the problems? Of course, storage and computation issues, privacy and ethical issues, personal information, images are sensitive for sure. The pre-processing is not trivial. It requires reduction in some cases. You need to resize. You need to remove objects. Sometimes we need to rotate some of the figures in the image. So there are multiple things that are required here. Okay, so let's check our example. So when you open the notebook, this is a very common example. So from TensorFlow, I'm using this dataset fashion mints. So it has images about clothes. t-shirts, shoes, sandals, things like that. So okay, so here we load the data and we split it into in train and test. We're not going to create models. So we have the labels. There are 10 different products here, or 10 categories: t-shirts, trousers, pullover, dress code, and the last one is boots. Okay, so when we have all the information, so we analyze like our data. Remember the how many observations we have, and also the size, because we know the pixels. So in the training set, there are 60,000 images, and in the test set, there are 10,000 images. Now each image is 28 by 28. So this is the height, the width. So the number of pixels per image is just the multiplication between these two. It's 28 times 28. That will give you the number of pixels, right, in a single image. So let me just multiply here real quick. 20 by 28, it's 784. So for each image, in this case small, we have 784 variables. Now, if let's say you want to add color, this is not the case, but if let's say that we have the RGB, so times 3. So that will increase from 784 to 2352. Okay, so from this data, I'm going to plot only the first one. So this is, okay, it's not 0, this is 1. So this is the second image in my data set, but you can explore with this. If you run the whole thing, you can change it just for the first position will be 0, the second one is a 1. You know that, right? So in this case, it's like a t-shirt, I guess. So that's our first image, our second actually. Well, let's plot the whole thing. This is a sample. This is a sample of some of the images, the first 25 images in our data set. So we have, this is the one that we preview in the previous one, right? This one. So here we have the image and the label. So this is a boot, t-shirt, right? So we have all the information here, just to get an idea on how it looks. All right, we know the labels uh, because we know this information, right? There are 10 classes, so 10 categories. Okay, so things that you will do. We explore the site, we visualize our data set, we get an idea of how it looks, also the labels. So typically what people do with this data set is to to create classification models. It's like giving an image. So what type of clothing is this? Is this a boot? Is this a t-shirt? So first thing that you check in an EDA, some of the things that you check is the class distribution to see if it's balanced or unbalanced. In this case, this is perfectly balanced. That's because this is an inbuilt data set, but in real life, it will be, more common that it's unbalanced. So you need to check that. But again, here is like we have 6,000 of each in the training set, and there are there are 10 classes. So in total, there are 60,000 observations. Again, this is perfectly balanced, so there are no issues over there. We can then check the pixel distribution. So for that, let me show you first how it looks. Okay, so here I'm flattening the data. But before I flatten the data, so let me just, I think it's best if I run everything, even though it's gonna disappear. So before I flatten the data, the way this is gonna look is that, remember that each image is 28 by 28, right? 28 by 28. So we will have an array that has 28 arrays inside. So it's like the first row, comma, then another array, which is going to be the second row. So it's a matrix that we have here, right, initially. And when we use the flatten, it's because we want to decrease the dimensionality from 2 dimensions of the original array to only a single dimension. So it's going to collapse the whole thing. This is how it looks. Okay, let me show you first the original version like this. So he's saying, okay, this is the first image, which is a boot, and there is an array 28 by 28. If I ask to show data, this is how it looks. So look, there is an array that contains multiple arrays. So the first one inside is this one, So we have 28 values here. These are zeros. That means that like that line, of the 28 pixels is black. That's so same thing with the next one, with the next row, and that's normal because remember that this is a, in this case, a shoe. So this initial part is it has a different color. All right. So once you get an idea of how this data looks, when you're gonna train the model, so typically you flatten the data. So the flatten means that we're gonna, instead of having like a two-dimensional array here, we're gonna collapse this and create a single one. So look at this, there is a single array. Now we don't have like the, like the other brackets inside. It's just a single array, it's a 1D object. So we use this object now. If you want to train the model, that's what we use. We need to flatten the data. Same thing here, to create the histogram. This is for a single picture. This is for a single picture. So for the first picture, like the one that is in the first position, that the boot that we just analyzed, so we flatten the data and then we see the pixel distribution. So you see like most of the pixels are zeros in this for that specific image, right? And of course there are others that are close to 50, between like 150 and 250. That's for the single image. You can do the analysis for the complete data set. So here, for example, we have like all training images and we flatten the whole thing. So we collapse them in a single plot. And now you see that most of the pixels in our data set are zeros, right? So you see the distribution of the data. You see the distribution of the data. So there are some, like in some cases, it's very common that you will see that the variables are normalized or standardized. That's common, like in the pre-processing stage. All right. Uh, what the last thing that I want to show you here is like you can perform a PCA here to reduce the dimensionality and to visualize your data. Remember that the original purpose of this data set is to be able to classify them, right? The 10 classes, the 10 type of objects that we have here. So before we create the model, which we're not going to do in these videos, that's not the purpose. But in the EDA, it's possible to visualize in 2 dimensions if it's possible to classify them or not, if there are differences in some of the cases. Again, remember that when you perform a dimensionality reduction, you lose some information. That's normal, right? Because you're going from an original space with multiple variables, 700 something, to just two variables or two principal components in this case. So we perform the principal components for with two components because we want to visualize in two dimensions. And the colors here represent the classes. So from 0 to 10, it means the different 10 objects that we have in our images. I'm pretty bad with the colors, but you can see that there are some colors that are clustered together, like the orange here, right? This in different sides, you will see different areas. For example, here there is another color. So it means that some objects, right? Some type of clothes are going to be easy to, not easy, but at least it will be possible to classify them because they are clustered, right? So that's the idea. That's what we're identifying here. The problem is like if you see a complete mess, like everything is overlapped and you don't see, like same colors together, then that's a problem. That means that it's going to be difficult to to represent, or maybe the reduction is not good. It's not capturing the whole thing. I'm not analyzing this because I don't have time, but of course you can check like what percentage, the complete variability you are representing with the two components. So the explain variance, right? Okay, so I'm gonna close the video for now, the class for now, but I wanted to emphasize how important is to increase your toolkit and to be open to analyze different data types, not just numbers, not just categorical variables. It's important to add text, images, videos, and audios, right? Because that's real life, and as human beings, we do that all the time, just in a normal day. Every time you are using different data sources, like you're getting, if you're, for example, you're watching this video right now, so you're visualizing, so you have like a video, right, or images, but at the same time you're listening to what I'm saying. So those are like two different data types, right? Audio, video, or images too. And there is also some text, right, which you are reading and processing, right? So we're able to do that. We assimilate different data types, and we use that. We combine them without an effort, right? And we use them to make decisions, to learn. Same thing we have to do with our problems. So problems are not just numbers and categorical variables. Real problems involve multiple data structures. So it is important to have, like different tools to ensure that we make good decisions. All right, I'll see you in the next video.